The Transmission Control Protocol, TCP, provides a communication service at an intermediate level between an application program and the Internet Protocol. It provides host-to-host connectivity at the transport layer of the Internet model. TCP works with the Internet Protocol, IP, which defines how computers send packets of data to each other. Together, TCP and IP are basic rules defining the Internet. TCP is a connection-oriented protocol, which means a connection is established and maintained until the application programs at each end have finished exchanging messages. It determines how to fragment application data into packets that networks can deliver, sends packets to and accepts packets from the network layer, manages flow control, and, because it is meant to provide error-free data transmission, handles retransmission of dropped or garbled packets, as well as acknowledgement of all packets that arrive. Let's see the connection-oriented error-free communication of TCP in an example. When a web server sends an HTML file to a client, it uses the HTTP protocol to do so. The HTTP program layer asks the TCP layer to set up the connection and send the file. The TCP stack divides the file into packets, numbers them, and then forwards them individually to the IP layer for delivery. Although each packet in the transmission will have the same source and destination IP addresses, packets may be sent along multiple routes. The TCP program layer in the client computer waits until all of the packets have arrived, then acknowledges those it receives and asks for the retransmission on any it does not, based on missing packet numbers. Then assembles them into a file and delivers the file to the receiving application. The TCP three-way handshake is the method used by TCP to set up a connection. TCP's three-way handshaking technique is often referred to as SYN, SYNAC, ACK, because there are three messages transmitted by TCP to negotiate and start a TCP session between two computers. This three-way handshake process is also designed so that both ends can initiate and negotiate separate TCP socket connections at the same time. That means the connection is full duplex. Oh, you know what? We have to take a break at this point and talk about TCP flags. There are 1-bit flags in TCP headers, which are called TCP flags. TCP flags are used within TCP packet transfers to indicate a particular connection state or provide additional information. Ignoring ECE, CWR, and NS flags for now, there are basically 6 TCP flags. The SYN, or synchronization flag, is used as a first step in establishing a three-way handshake between two hosts. Only the first packet from both the sender and the receiver should have this flag set. The ACK flag, which stands for acknowledgement, is used to acknowledge the successful receipt of a packet. The RIST flag, which stands for reset, gets sent from receiver to the sender when a packet is sent to a particular host that was not expecting it. The FIN flag, which stands for finished, means there is no more data from the sender. Therefore, it is used in the last packet sent from the sender. The PSH flag, which stands for push, is somewhat similar to the URG flag and tells the receiver to process these packets as they are received instead of buffering them. The URG flag is used to notify the receiver to process the urgent packets before processing all other packets. So every legitimate TCP connection begins with a TCP three-way handshake, which is used to exchange sequence numbers so that lost packets can be retransmitted and packets can be placed in the proper order. If machine A wants to initiate a connection to machine B, it will start by sending a TCP packet with a SYN control bit set. This packet will include an initial sequence number, which I'll call here ISNA, because it comes from machine A, which is 32 bits long and typically generated in a pseudo-random fashion by the TCP software on machine A. The ACK number, another 32 bits in the TCP header, is typically set to 0 because it is ignored in this initial SYN. Some operating system variants may make this ACK number non-zero, but either way, it's ignored by the destination machine. So if the destination port is open, that is, there is something listening on that port, it must respond with a SYN ACK packet back, a packet that has both the SYN and ACK control bits set at the same time. This packet will have a sequence number of ISN B, a pseudo-random number assigned by machine B for this connection. The SYN ACK packet will have an acknowledgement number of ISN A plus 1, indicating that machine B has acknowledged the SYN packet from machine A. To complete the three-way handshake, machine A responds with an ACK packet which has a sequence number of ISN A plus 1. It's the next packet, so the sequence number has to change from the value in the original SYN packet. The acknowledgement number field is set to ISNB plus 1, thereby acknowledging the SYN ACK packet, right? So we have now exchanged sequence numbers. All packets going from A to B will have increasing sequence numbers starting at ISNA plus 1, going up by a value of 1 for each byte of data transmitted in the payloads of A to B packets. Likewise, all responses back from B will have sequence numbers starting at ISNB plus 1 and going up for each byte of data from B to A. In essence, we have two streams of sequence numbers in this series of packets, one from A to B, originally based on ISNA, and the other from B to A, originally based on ISNB. Perfect.